I am here to talk about how AWS does serverless. So just to get a sense of the audience, how many people have used the AWS site before? Okay, awesome, a lot of you. So for the people that have, what you've been using with the site has been completely serverless. There's no EC2, there's no containers, there's no nothing, right? It's all predominantly running off Lambda functions and a whole bunch of other services, right? So we've been like that for the past 4 years since we've been started. We haven't actually had any EC2s or any containers or anything like that in the entire platform. It's been completely serverless. Who am I? I'm a software development lead at AWS. I've been around, I think I was one of the second developers who's worked on the platform. So I've seen some things over the course of the past 4 years. I was using serverless when one of the very few ways to manage it was just using, like, clicking around with the AWS interface to manage Lambda deployments and stuff like that. I myself have been developing JavaScript full stack for around 4 years as well, so doing that on the front end and the back end. All of the Lambda functions are all using Node. So a lot of people today have talked about, like, serverless theory, right? Like, what is serverless applications, how do they work, and so forth. But I'm mainly going to be talking about what a serverless platform looks like in production. So, yeah, cool. So, okay, so just to give you a sense of the scale we're running at, so AWS Guru at the moment is roughly pulling around 120 million Lambda invocations monthly. So just to put that in perspective, that's around 100 invocations per second. We're pulling around 180 million API gateway calls, so that's around 70 a second. And our CloudFront usage is around 90 terabytes a month. So we're a video delivery company, so we spend a lot of our bandwidth delivering those resources to you guys through CloudFront. That has doubled roughly since last year, and one of the best parts of the fact that that doubling is that we noticed nothing. We didn't have to do anything to handle that doubling. It was just completely elastic. So that's been awesome. We've gone from 1 developer 4 years ago now to around 25 developers with around 5 teams. So we've grown quite a lot. So what I want to do is I want to be able to give you guys the overview of the architecture, some of the challenges that we've faced over the 4 years, talk about those challenges in the perspective of the way we lay out our microservice, their composition, talk about how we manage service-to-service calls, how we do front-end to back-end communication, all of those sorts of things. So the overview of our architecture, we have users use our site. We use isomorphic rendering, so we use a technology called Next.js, which is basically a technology which sits on top of React and allows you to render certain parts of the website on the back end before delivering the HTML to the front end. Next.js generates that React by calling through to a GraphQL proxy. We use GraphQL throughout the entire platform. The proxy is like a facade that sits over the complexity that is all our microservices. The proxy, when the request comes through, gets delegated to the various microservices based on which microservice can resolve the query or handle the data request. So this is just one request in from the backend, goes to the proxy, and then the proxy calls the various microservices that it needs to be able to satisfy that request. One of the important things here is that we're running GraphQL or GraphQL.js on top of Lambda through API Gateway. And then those other services may communicate to other microservices based on the data requirements. So the first part is the composition of the microservices. How are the microservices laid out? How do they look? The next part is going to be talking about how do those microservices communicate between each other, what are the mechanisms they use, and then the third part is the front-end to back-end communication. How does that look? How does that work? Okay, so the two biggest challenges that we face with serverless architectures are predominantly around latency, so making sure that serverless applications are responsive, they're not taking too long to load the page, and the other problem is some limitations around what kind of services we can use within the AWS ecosystem. So one of the things that is a particular challenge is if you want to use any kind of SQL database, you have to put your Lambda in a VPC, and the implication of a cold start within a Lambda and a VPC can be quite long, so 7 seconds. So that's really kind of constrained us to thinking outside the box and not using some kind of RDS or some kind of relational database. So a lot of our technologies are built on top of serverless ones like DynamoDB and S3 and so forth. So yeah. So microservice layout and composition. How do our microservices look? So a lot of what we do with our microservices are predominantly just API calls, right? So a request comes in from the client, hits GraphQL, and then the Lambda function processes that request. So that's like the API part. So this doesn't include any kind of state, right? For an API to actually be useful, you need to be storing and processing data. So the anatomy of our microservices, we split them up into 3 layers, the way that we just think about these, so we can manage each layer differently and just conceptualize them in the way that they should be conceptualized. We first have a stateless layer. So the stateless layer are Lambda functions that are being used as a part of like integrations and also the API. So in theory, you could kind of just delete this layer and then bring it back up, and there wouldn't be too many problems. The next layer is mainly around the stateful resources. So this is where we store our DynamoDB, our S3, SQS, Kinesis, and Algolia. I'll talk about Algolia later and how we use that. But this layer is something that you can't just like throw away, right? Like you actually have state in your application in this layer. It's not something you can just throw away. You need to be a bit careful about it. Like if you deploy some CloudFormation which deletes like an S3 bucket or something like that, or detaches an S3 bucket from the stack, you're in a bit of trouble. And then the last stack is the configuration and core dependencies. So this is really where we just store our remote configuration and stuff like that. And that all the other stacks depend on those parameters that we store in SSM. And it would also be the place where we also store like custom resources to perform custom actions that perhaps CloudFormation doesn't allow us to do yet. So yes. So that's how the anatomy of our microservices look. How do we manage service-to-service communication of various serverless microservices? So the common thing that you would do is just have service A call service B, right? And you have to somehow communicate between those two services. The way we do that is just very simply with GraphQL. So based on what I was talking about before, we have 2 microservices. They just have GraphQL.js, and then one microservice just makes a backend-to-backend GraphQL.js call into the other. One of the nice things about GraphQL is that it's like a typed interface for communicating between the microservices, whereas like something like HTTP doesn't give you those kind of abilities to type the interfaces. So you can actually do like introspection between the microservices to make sure you're not breaking that interface when you're performing some kind of deployment. One of the challenges we actually ran into in the early days, and I think Ben was talking about this before in his early speech, was people didn't really know how to layer their Lambda functions. Like in a 3-tiered architecture, you could have a Lambda that represent each tier in the architecture. You could have a Lambda for a specific piece of behavior. You could have a Lambda for a lot of various things. One of the challenges with this kind of model is the more Lambdas you have when you're running like a request response type of call, the more likelihood you are to run into cold starts and really jack up your P99s like through the roof. So one of the challenges we had in our early days was we were having Lambdas call other Lambdas too many times. So in the case that you had some kind of cold start, you could be in a scenario where if you were just kind of loading a page, it would take 2.5 seconds because you hit cold starts among every Lambda function. When they were hot, it was kind of like fine. You'd have around 800 milliseconds, which is still pretty slow for a query, but the 2.5 seconds is the real problem here. We lowered that by basically making sure that for a given microservice that responds to APIs, we just made it one microservice or one Lambda function, right? So we have one handler in a given microservice process the entire GraphQL query, and that worked out really, really well because that meant that when you were processing just one request and all you needed with one microservice, you only have one Lambda invocation. So that was good. That shrunk the potential call call chain that you could have from Lambda to Lambda. So if you need to go from microservice A to microservice B, worst case, you have a 400 millisecond cold start to be able to deal with the query. Best case, it's around 200 milliseconds. So that's not so bad. No, the other way. So another way that you could deal with this is by data replication. So in certain circumstances where it makes sense, you could have the two microservices, and data from microservice A could be replicated in some way in microservice B. And the way that you could handle that is by just replicating it, maintaining some kind of cache or something like that. And to do that in a nicely decoupled way, you could use the SNS SQS pattern. So say a mutation comes into service A, it transforms some data. Service A could push a request to service B's SQS queue. Microservice B could cache that data in some capacity, and then when the request comes in to service B and it needed the data from service A, it could just process it there within the one Lambda function. So this means you don't have to do like 2 calls between microservices, and you don't have that potential for hitting 2 cold starts between microservice communication. So that's the way that we handled API-specific stuff. From a data side, so the way that we do data warehousing is, at the moment, we have DynamoDB tables, and they're ETL directly into a Redshift database, and we do that with AWS Glue, and AWS Glue pulls those tables in periodically into the warehouse so that we can perform SQL queries. So while most of our microservices, well actually all of the microservices don't have any SQL databases, we still need to perform some kind of SQL specific queries, particularly for warehousing and stuff like that. So when it comes to actually performing those reports, we want all that data in one place. So we just periodically pull that data out of all the microservices databases and then push it into Redshift. The other case is we heavily use Segment for a lot of stuff. So Segment's just this kind of like event bus that you can just push events to. And Segment will periodically push the data into the warehouse. So we don't have to deal with any of these VPC concerns. So how do we manage front-end to back-end communication? So a pattern that we really like is just, if you can skip calling Lambda altogether to resolve your query, try doing it, right? If you don't have to call into Lambda, you don't have issues with cold starts. One of the things that we use for a lot of our site when we need to perform complex querying or search or something like that is a service called Algolia. Algolia allows us to achieve those kind of complex query requirements. So what happens is a mutation comes in, you need to change some data in your data store, that goes to Lambda. Lambda will then write that data into DynamoDB, and we use a DynamoDB stream to basically give us a change log of all the changes that have happened within a DynamoDB table, and that Lambda will then go and update an Algolia index. So that Algolia index is just like a replica of our data that the browser can access directly without having to go through a Lambda function. Algolia is awesome, it's really, really quick, so for certain parts on our site that load really, really fast, you probably are hitting Algolia directly. And just to put it in perspective, it's around 20 milliseconds to make a call into Algolia. So one of the things I was saying before is each of the microservices expose a GraphQL interface. What we do basically to deal with the complexity of all these microservices exposing their own interfaces is we provide another GraphQL service which sits on top of those, which is like some kind of proxy layer that sits across all our backends. And what that does is it basically stitches all the interfaces of all the microservices together and gives you one nice URL that you can query. One of the nice things about this is what happens is when a query comes in from the client, hits the proxy layer goes and tries to resolve that query from all the microservices closely to the backend, right? So one of the challenges with REST is that you fetch one entity and then you look at the data from that entity, fetch another, and then you fetch another and so forth. So you got a lot of these round time trips. The advantages of using like a GraphQL proxy is that you kind of keep the joining of that data really close to the source of the data. So that means that kind of like multi-entity join happens closer in the database, which means it can be resolved faster. So, and then this is where Next.js comes into it. Next.js can hit the proxy, and then the proxy delegates down to the microservices to resolve queries. We predominantly use those isomorphic rendering for SEO concerns, just because we want to make sure that when we're serving up our pages to Google, they're all rendered HTML, so the Google crawler doesn't have to parse all the JavaScript and then run it and then get a snapshot of the page, right? We're actually serving up the page to the crawler right as they hit it. Cool, so the two biggest challenges with completely serverless architectures is latency. We've predominantly solved that through replicating data between the microservices, limiting the amount of Lambda to Lambda invokes, so we don't have these long Lambda call chains, hitting third-party services directly from the front end directly if you can avoid it for certain queries, just avoiding VPC-specific services altogether. And then we solved a lot of the problems of not having RDS-style databases by using a serverless service like Algolia. So that's an overview of our architecture, and thank you very much.